So this is the first of a few lectures where we want to discuss Bloom filters. And so by way of review, let's think back to what we were just talking about, which was hash tables and hash functions, and how randomness enters into the picture of how we can use hash functions to spread items out evenly across the buckets of a hash table. So we have our hash functions that map a large universe of possible items into this smaller range of buckets of a hash table. We said that once we start using hash tables, if we want to make interesting statements about the occupancy of that hash table, like things like how many of the buckets are empty, or what's the maximum number of items per bucket with high probability, things like this, that we absolutely need probability, and we need to model things using probabilities, random variables, the sorts of ideas that we discussed in the previous lectures. And we talked about the key models here, like balls and bins, and then things that could be considered special cases of balls and bins, which we'll see in much more detail later. And the hash functions themselves are drawn from these random hash families before the data arrives. So equipped with these same ideas, where we have hash functions and we have arrays or tables of slots that the hash functions map items to, we can actually take this idea to a kind of extreme where instead of storing a set or a map and doing so with full precision, where we can never make a mistake, right? If we go to query whether an item's there, and we added it previously, we'll definitely find it. If we go to query an item that's not there, we'll definitely find out it's not there, right? So we had full precision. Everything that we did was deterministic, and we knew we were going to get right answers to our queries. What we'll see here is if we can relax the requirement that we are definitely going to get the right answer to our query, and if we limit our attention to sets rather than maps or associative data structures, then we can use way less space per item. And we can do this in a way where, with a little bit of work, we can establish that there's a pretty good and an adjustable guarantee that we're going to find the right answer. With the probability that we're going to make a mistake is something that we can tune to be extremely low. Okay, so let's explain what this Bloom filter idea even is. So let's start with our familiar picture of a hash table using chaining. Here it is. And the way I'm going to approach a Bloom filter is I'm just going to take things away one by one. And the first thing I'm going to take away from the hash table is the parts that are highlighted green, which is representing where we store the values. So remember, what's a key, what's a value? The keys are the items that we're adding, and the value is the data associated with that key. Right, so maybe the key is a unique ID, but then the value is a data record pertaining to that unique ID. Like maybe the key is your social security number, and the value is your age, or the value is your bank account balance, or whatever it is. Okay? So we've got this data structure that at the end of the day really just consists of slots that hold keys, and slots that hold values, and slots that hold pointers. And I'm suggesting the first thing we can get rid of is the slots that hold values. Once we do that, we have a simpler picture. Values now grayed out. The values are gone. I took them away from the triples. But of course now we no longer are able to store a map. This data structure represents a set. Okay, only a set. We don't have a way of associating values with the keys, but we do have a way of keeping track of what keys we've seen. So this is sort of, if you have programmed, let's say you've programmed in Java, then you've seen that there's a difference between a data structure called hash map, which you can use to store a map, versus hash set. And this is basically what we just did, is we converted a hash map into a hash set by getting rid of the places where we would have stored the values. In C++, this would be the difference between unordered map and unordered set. And in Python, this might be the difference between a dictionary and a set. Okay, so now we have a hash set. So the next thing, so I took away values already. So what am I going to take away next? I'm going to take away the keys. And this seems absurd. You know, what do you mean? The keys are all that's left, right? Not quite, because I am going to take away the keys, but what I'm going to leave is kind of this shadow here of which buckets were the ones that had non-empty linked lists coming off of them, right? So which were the buckets that had any items in them. So I have preserved that information. So I'm not actually going to use pointers to represent that information because I don't need them. I really just need for every bucket to distinguish whether there was nothing or there was anything. And so for that, I really just need bits. And so now I've taken what used to be a hash table with chaining, with keys and values. I took away the values. And that meant that we could only store a set. Then I took away the keys. Now I'm left with this, and I haven't yet really described how and if and why this can be a useful data structure. So let's talk more about, okay, this is the data structure, but how do we actually use it? Why is it useful? Okay, so let's imagine that we are going to build one of these Bloom filters from a data set. And the first thing we do is we allocate an array of bits, a bit vector or a bit array, and it's going to be all zeros to begin with, corresponding to the intuition that if we were populating a hash set, the set would be empty to begin with. So we're going to start with a bit vector with all zeros. Then what's going to happen is in order to add an item to the hash table, in order to add an item to the Bloom filter, of course, I'm going to do what I always do to begin with, which is take its hash, put it through the hash function. So let's say I apply hash function h sub 1 to the first data item in the data stream called x sub 1, and it ends up mapping to this fourth bucket. Okay, this fourth slot in my bit vector. What am I going to do? I'm going to set it to 1. So it was initially 0, but if I add an item, I'm going to set it to 1. And that's how I insert an item. We'll talk more later about what happens when I have multiple hash functions, but for now just assume we have one, and therefore the process of inserting an item is just a matter of calculating that item's hash value, going to that offset in the bit vector, and setting that position to 1. Okay, so that's the insert procedure. I say set the bit to 1 if not already. If it's already 1, we do nothing. Okay. So let's say I've done this, and I've done this for 3 different items. X sub 1, X sub 2, X sub 3. They've all gone to different buckets. Those are the 3 slots containing a 1 in this picture. And now let's say a 4th item comes along, and I hash it with my hash function, h sub 1 of x sub 4, and x sub 4 goes there, to the same slot as x sub 2 went. So this is a collision, of course. What do? Well, like we said before, if the item's already set to 1, we do nothing. It might be already set to 1 because we've already added this exact item before, x sub 4. Or it might be set to 1 because of a collision, because of a different item that we added previously that just happens to have the same hash value. Either way, we do the same thing, which is nothing. If it's already set to 1, we do nothing. It might be a collision, but like I've written here, if it's a collision, life goes on. It means that we will potentially make mistakes later, which we will analyze in some depth. But there's nothing corrective for us to do. We're just going to live with the fact that we have a collision. Okay? So how do we query the Bloom filter? So what did we just do? We just added a bunch of items to the Bloom filter. This now, you have to imagine I've added a bunch of items because you can see there's now a bunch of 1s in that bit vector. We added a bunch of items. Maybe we had some collisions. And now we want to ask the question of whether a particular item was one of the ones we added to the Bloom filter. So how do we ask that question? Well, just like with the hash table, we of course are going to use the same hash function that we used to insert the items. We're going to use that hash function to hash the query item, and then we go check to see if that bucket is set to 0 or 1. So for example, let's say we are querying the hash table using our familiar h1 hash function, and the data object, the item that we're querying is called y, and let's say the hash function sends me here, right, where there's a 0. So if that happens, what do I know? Is the item in the set or not? It's not. It can't possibly be in the set. If the item were in the set, we would have set that bit to 1. Right? Remember that our procedure for inserting items only involves changing 0s to 1s. We never change 1s back to 0s. So there's no way that this data item y could have been one of the ones that we inserted previously. Okay? But now let's say we're going to query a different key called z. And now the hash function sends us to an element that's already set to 1. So the question we have now is, does this mean that the item was one of the ones that I added? Does this mean that z is one of the items that we inserted? And the answer, of course, is maybe. It's not necessarily yes. Why maybe? Well, because we can't rule out that this is a collision, right? We can't rule out the possibility that z was not any of the keys that we inserted, but one of the keys we inserted by coincidence went to the same slot of the Bloom filter as z. Okay, so if the filter says 1, if the filter has a 1 at that position, then the item may be present. Or it may be a collision. But what's interesting here is, if the answer is 0, we know the answer, if the bit that we query is 0, we know that the answer is no, for sure. We know that, for sure, the item was not one of the ones that we added to the Bloom filter previously. If the answer is 1, that's where the uncertainty creeps in. That's where we might be, the answer is maybe, right? But that ambiguity only exists if we see a 1. Right, so it doesn't exist if we see a 0. We're sure of the answer if we see a 0. So this is what we would call one-sided error. We can make a mistake, but we can only make a mistake in one direction. And that's a good thing, because when we can only make a mistake in one direction, then we can use another tool at our disposal, which is the randomness in the hash functions, to try to drive down the possibility that we make an error. Right, so algorithms using randomness can attack one-sided error with repeated trials. Basically, if I'm not sure whether the answer to my question is yes or no, but I know, if I see a 1 and therefore I'm not sure if the answer to my question is yes or no, but then I repeat the whole thing again with a new hash function and the answer is still 1, well, that makes me even more confident. And then if I repeat the whole procedure a third time with a new hash function and the answer is still 1, I'm even more confident. And on the other side, if I now repeat the experiment with a fourth hash function and now the answer is 0, I'm sure the answer is no, right? So that's the magic of combining randomness with one-sided error. Right, so here's basically that idea that I just proposed, is that we might want, since we have one-sided error and we have randomness, why not go through an exercise where I have not just one of these Bloom filters, but I have 3 of them. Now we're sort of departing from the hash table metaphor a little bit, right? With hash tables, we only ever had one table. But now we're going to entertain the idea that maybe we have multiple Bloom filters. And the idea is we're not just going to repeat the same hashing procedure for each Bloom filter. We're, of course, going to have a different hash function for each of the 3 Bloom filters. So let's say we have h sub 1, 2, and 3. And so when an item is being inserted into this array of Bloom filters, into this collection of Bloom filters, let's say that we insert that item in all the Bloom filters. So if the item x sub 1 comes along and h sub 1 maps x sub 1 to here, then we'll set that to 1. But then we also use h sub 2 to hash x sub 1, and maybe h sub 2 sends it here, and maybe h sub 3 sends it here. Okay? So what if we did this with k, not letting k be a variable? What if we did this with k hash functions and k bit vectors, essentially k Bloom filters? So here's sort of a study question. Will all the filters have the same number of set bits? If I apply this procedure, in other words, I have k Bloom filters, k bit vectors, and a set of objects comes in and I hash every item and I insert it into all k Bloom filters. Okay. At the end of the day, will all of those k Bloom filters have exactly the same number of set bits in them, of bits that are set to 1? Well, no, not quite. It's not a guarantee, because even though I've added the same number of items to each of the Bloom filters, we don't necessarily get the same pattern of collisions. Right? So the other concern we have to take into account is different hash functions are going to induce a different set of collisions. So for example, if h sub 1 happens to have no collisions, but h sub 2 has 1 collision, then of course h sub 2 will have 1 fewer set bit compared to h sub 1. So not necessarily. So on average, they'll have the same number of set bits, but not precisely. Okay. So let's say I've used k hash functions to create this array of k Bloom filters, and now I would like to query this array or this collection of Bloom filters with item y. And let's just say that the hash functions 1, 2, 3, and k, for the filters that I'm actually showing on the slide, end up mapping y to these 4 positions that you see here. Notice 3 of them are set to 1, 1, 1, 1, but 1 of them is set to 0. So what can we conclude about whether the item y is one of the ones that we previously added to this array of Bloom filters? We can conclude that it definitely was not one of the items that we added. Had it been one of the items we added to these Bloom filters, this would be a 1. Right, so we know that y is not one of the items that we added. So if any of the queries, any of the k probes, lookups in these bit vectors gives the answer 0, we know that the item is not in the set. If all of the k probes into the bit vectors give the answer 1, so I'm showing 4 of the bit vectors here, but just imagine in this ... I've got several more bit vectors, and the answer is 1 in all the bit vectors. So if all of those queries yield 1s, then the item, just like before, may be in the set. Right? Just like when we were just using one filter and one hash function, it's still the case that the item may be in the set, or it could be k coincidences, right? It could be k collisions, right? We could have collided in all k of the Bloom filters. But you get the idea that we've sort of defended against that possibility a bit better by having k Bloom filters instead of having one Bloom filter. And in fact, it's not too hard to analyze what we've done. So let's say, for example, that we are querying with an item that is not actually present. It's not one of the ones that we used when we inserted items into our array of k Bloom filters. We can ask the question, what's the chance that all k of the k Bloom filters are going to return a 1? Right, so again, this is a situation where they quote-unquote should be telling me 0. Right? The item is not really one of the items that we added to the array of Bloom filters. But as we know, there's the possibility that we had a collision in all k Bloom filters. So what's the probability of that? The probability of a collision in all k Bloom filters. And let's say, so k is the number of Bloom filters. Let's use a variable p sub 1, which is just basically what's the fraction of bits in the Bloom filter that are set to 1. Okay? All right. So what do I write here? I guess in each Bloom filter, p sub 1 is the chance that a random hash function, a random probe, right? Essentially, this hash function is giving us a random place to look in each of the Bloom filters. So the chance that a random probe in a given Bloom filter is going to return 1 is nothing but the fraction of the bits that are set to 1. Right? So it's p sub 1, but the chance that we hit a 1 in all k of the filters is now k repeated trials of that same attempt, right? So I need to put k in the exponent. right? So it's p sub 1 to the k is the probability that I encounter a 1 in every single filter. But the key is that p sub 1 is a fraction and k is in the exponent, right? So if we have control of k, that means we can take what initially might be a fraction like 1/2, for example. So let's do an example where the fraction is 1/2, and drive that from 1/2 down to a very, very small fraction very quickly, right? So let's say that p sub 1 is 50% or 1/2, and so 10 filters. So now the thing we have to put in the exponent is 10. So we have 1/2 to the 10th power. So that's going to be 1 over 1024, or a bit less than 0.1%. So even though the false positive rate, the fraction of set bits, and therefore the false positive rate with respect to a single filter, even though that's 50%, well, when we do it for 10 filters, then it ends up being a very low number. We've driven it down basically exponentially quickly, k being the number in the exponent. So let's make one more refinement, and then let's talk about how big this data structure is that we've made before moving on to the next video. All right. So in practice, even though I showed you arrays of several k Bloom filters, separate Bloom filters, a more common thing to do is to just use one big bit vector, one big array of bits, maybe k times larger than you would have used if k was equal to 1, but some big bit vector, and then use all k hash functions at once, just with respect to this one Bloom filter. In other words, let's say k is equal to 4, and we have an item x that comes in that we would like to insert. We would apply all 4 of the hash functions, but then all 4 of the hash functions would map us into a slot in the same bit vector, just different slots in the same bit vector. Different slots, or maybe not, right? There might be collisions among the hash functions in the given bit vector. But in this example, I have 4 hash functions, and I've set 4 of the bits in my bit vector to 1. Okay? This is very similar to the suggestion that we just have 4 separate bit vectors, each with their own individual hash function, but it ends up being a little bit more efficient in terms of space and simplicity. Right? So if I wanted to do an insertion, this is what I would do. I would apply all 4 hash functions. I would set those 4 bits to 1. Then if I wanted to do a query, I would of course do kind of the mirror image thing, where I would apply all the 4 hash functions and look up all the values at those 4 places. If any of them are 0, the answer is no. If all of them are 1, the answer is maybe. Okay? So similar in spirit to that array of k Bloom filters, but actually it's all one big filter, but k hash functions. So okay, so before we move on, let me just let's remind ourselves of why we're even going through this exercise of tolerating possibly getting the wrong answer to our query. It's to save space. We want to do all of this so that even if the set that we're trying to represent is a very large set, we might still have some hope of being able to store a Bloom filter representation of that set, which is an approximate representation of that set in, for example, memory on a typical computer, or in some favorable part of the memory hierarchy on a computer. Maybe you're trying to fit it in memory, maybe you're trying to fit it in last level cache, or you're trying to fit it in L1 cache or something. But you can fit it. So how much is this savings, though, really? Like, how much were we really giving up in order to achieve this? Let's just do a back of the envelope comparison of a Bloom filter, shown here, and then a hash set, shown here, using chaining, like we discussed before. And let's assume for a moment, it's not a great assumption, but let's assume for a moment that the Bloom filter here and that hash table here have an equal number of slots. So for every slot in the hash table, and each slot in the hash table, recall, is a pointer, or something like a pointer. For each of those pointers, we have just 1 bit in our Bloom filter. Okay, so let's think of how much space is being taken by the hash table. Okay, so let's first focus on all these elements that are in the linked lists that are hanging off the buckets. We're going to ignore the buckets themselves for a moment. Just think about the items that are in the lists? Well, for every item that we added, and let's say that overall there were m items, right? So there are m keys. In other words, there are m of these pairs. For each of those items, I'm storing what? Well, I'm storing the item itself, and I'm storing a pointer. Now let's just make an assumption that the amount of space that I need to store an item, the key itself, is also about 1 pointer's worth, right? Just a simplifying assumption. So if it's about 1 pointer's worth, then what do I have here? I have 2m pointers worth of data, right? 2 pointers for each of the m keys. Then what do I have here in my, what do I have here in my array of buckets? Well, I've got n pointers, right? Where n is the number of buckets, as usual. Okay, so what do I have in total in my hash set representation? Again, assuming that a key takes about 1 pointer's worth of space, I've got 2m pointers here and n pointers here. Now, what do I have in the Bloom filter? I have n bits. That's it. I'm not storing any keys. There's no pointers anywhere. It's just n bits. So the comparison between the two is I've got n bits over here, and I've got 2m plus n pointers over on the right-hand side. How big is a pointer? Well, in a typical modern architecture, it's 64 bits, say. So this could be the difference between hundreds of bits, small number of hundreds of bits over here, per n, per slot, hundreds of bits per slot, versus 1 bit per slot. So it's clearly a large savings. Now, this assumption wasn't a great one, right? Because in some sense, the Bloom filter and the fact that it can yield false positives means that we're more sensitive to the situation that maybe we didn't allocate enough slots for our data set. We really would like to see n be some multiple larger than m, the number of items that we're going to add. Whereas with the hash table, even though that same concern exists and it affects the efficiency that we could have querying the hash table, it's not a concern about whether the hash table is going to give the right answer or not, right? It's definitely going to give the right answer regardless of how many slots we picked. We might end up with unreasonably long chains, but that doesn't affect whether we get the right answer to a query. So in some sense, there's more at stake over here with making sure that n is substantially larger than m. But still, we're probably talking about a small constant factor, right? We're talking about n being some small constant, maybe 2 times larger than m, the number of items coming in. So while it does cut into our original calculation of hundreds of bits per n versus 1 bit per n, it cuts into that difference a little bit. There's still going to be a substantial difference even after we take that into account. So even if the number of Bloom filter bits that are needed is some constant factor times the number of hash buckets here, we're still talking about a major savings. We're still talking about the Bloom filter being a factor of, I don't know, 50, 60, 100, something like that, smaller than the corresponding hash set, using those assumptions that we made, like, for example, that the number of bits needed to store an item is equal to the size of a pointer.